square root of T over mu. Don't forget that. Let's now talk about energy transmitted by waves on a string. The vibrations of a stretched string can be compared to the simple harmonic vibrations of the loaded string. A segment of the string vibrating is exactly the same as the simple harmonic vibrations of the string of the loaded string. All right, tell me, what is the total energy of vibration of this? What is the total energy of vibration? You remember the equation? Equal to 1/2 Ka squared. Now, the energy of vibration of a loaded spring is 1/2 Ka squared, where, I hope you remember these, K equal to m omega squared. You remember that one? Well, the first time I introduced this, you know that omega equal to square root of K over m. Therefore, K equal to m omega squared. If you square both sides, is that right? We get omega squared equal to K over m, or K equal to m omega squared. So we will now use energy of a vibrating segment of string. In place of K, we will use m omega squared. If mu is the mass per unit length of the string and delta x is the length of the vibrating string, then K equal to m omega squared. What will m become? If mu is the mass per unit length and delta x is the length of the string, then mass m will be mu multiplied by delta x. You see, K equal to m omega squared mu delta x omega squared. And therefore, the energy delta E of this vibrating piece of string can now be written as delta E equal to, remember we're using the same equation, 1/2 Ka squared, where K is mu delta x omega squared. So that will be 1/2 K. K is mu omega squared delta x. Watch, I have rearranged it slightly. Mu omega squared delta x stands for K, and Ka squared now become mu omega squared A squared delta x. And that is the expression for the energy of vibration of a stretched string. Now, delta x, the length of the string, equal to V times delta t. Is that right? Where V is the speed. Speed multiplied by the time will give you the distance. So I'm going to replace this delta x by V multiplied by delta t. And what does the equation now become? Delta E equal to 1/2 mu omega squared A squared V delta t. Delta x is replaced by V delta t. Well, power P transmitted by the wave is the rate at which energy is transmitted. In other words, if I divide this delta E by this delta T, delta E by delta T is the rate at which energy is transmitted. That will give me a measure of the power transmitted. Power transmitted is delta E divided by delta T, which is 1/2 mu omega squared A squared V. A very important relation. The energy transmitted by a vibrating string is 1/2 mu omega squared A squared V delta T, where mu is the mass per unit length, omega is the linear frequency, the omega equal to 2 pi f. Is that right? Okay. Power transmitted is 1/2 mu omega squared A squared V. Again, mu is the mass per unit length. Omega is the angular frequency, which is 2 pi f. A is the amplitude of vibration, and V is the speed of energy transfer. Well, we will use the results we obtained in this lesson to solve problems in the second part of this lesson. So this lesson I'm going to call 1.2a, and then examples, worked examples will be 1.2b. Now, in the meantime, I would like you to go back and look through this lesson one more time and learn all the basic core concepts. All right? I will see you for the problem solving session a little later.